Hi everyone. Today's lesson is on something called the fundamental theorem of variation. And in just a minute, we're going to fill in the actual language of the theorem. But I think that the language makes it look more complicated than it really is. So I'd like to actually start, and you're welcome to write this down if you want to. But I just want to kind of talk you through what this theorem is all about and what it's trying to get you to understand about variation. So I'm going to start with a direct variation equation. So remember, direct variation is anything that's k times x. So I'm just going to pick a k value. I'm just going to say y equals 3 times x. Okay? And what we want to look at is the relationship, not necessarily between x and y, because that's what this equation is showing us, but what happens when we change the value of x? How does that affect the value of y? So let's say x equals 2 here for just a second. When x equals 2, if we were to plug in a 2, we would get that y equals 6. What this theorem is all about, what it's meant to have you consider, is if I do something to this x value, so let's say I'm going to take this x value and multiply it by 4, I want to know what does that mean will happen to the y value. Now I'm doing this with specific values of x and y, but this lesson is really going to focus on not giving you values of x and y and just asking you about this relationship. I'm just doing this to kind of illustrate the point here. So you'll notice that when x equals 2, if I multiply it by 4, that would give me x equals 8. When I plug 8 in here, I get y equals 24. And so remember, the big focus for today is what does that mean happen to my y values? Well, my y values also got multiplied by 4. This is the kind of the point of what we're doing today. And that might not be earth-shattering for you because you might be looking at it and going, well, of course, we multiplied this by 4, so we multiplied this by 4. That's because this is a real simple direct variation problem. Now let's change it up just a little bit. Let's say I'm going to do 3x squared. Okay, so that's still direct variation, but it's with a square on the variable. So let's do the same thing. When x equals 2, ask ourselves what y equals. So I would do 2 squared is 4, 3 times 4 is 12, so this would give me y equals 12. And so I'm going to once again take that x value and multiply it by 4. So I'm going to work with x equals 8. And the question I'm really asking is what does that mean will happen to my y value? Okay, this is the thing that I'm concerned about, is what will the relationship be between this y value and the new y value? Well, and of course I made myself use numbers that are bigger than I can do in my head, but 8 squared would be 64, so 3 times 64 gives me 192. So clearly this is a lot more than 4 times larger. The last time we did this, it was just times 4 over here means times 4 over here. This time it got a lot bigger than that. So let's take, I'm going to do 192 divided by 12 to figure out how many times larger this is. And we end up with 16 times larger. Okay, so what happened here? Why did this not happen? Why did it suddenly become a 4 and a 16? Well, if you think about 16, 16 is really equal to 4 squared. Okay, and our equation had a square in it. So when I multiplied my x value by 4, the effect on the y value was that multiplied by 4, but also being squared. Okay, so just to point this out, if I was working with the equation y equals 3x cubed, and I did this same thing, if I multiplied the x's by 4, I would expect the y values to get multiplied by 4 to the power of 3. Okay? That's what the fundamental theorem of variation is all about. So let's write that down in mathy language. So if y varies directly as x to the n, so that's what we did here. All of these examples we did were y varies directly as x to the n. By the way, notice this k value didn't matter to us at all. I could have put a different k value in here. Now that would have changed my x and y, well, it would have changed my y values, but this relationship would have stayed the same. So if I worked with y equals 2x, let's say, and I did x equals 2, that would give me y equals 4. If I quadrupled that and worked with x equals 8, I would expect this to still be multiplied by 4, okay, because it's just a single direct variation. So x equals 8 would be y equals 16, and so I still see that relationship there. So even though my y values changed, the relationship between them did not. Okay. And then if we come along and multiply x by a constant, so that was this guy here. The constant would be this, the times 4. Okay. Then what we're expecting to happen is y will be multiplied by that same c value, so by c, but the c will also be raised to whatever power was on the x. So y will be multiplied by c to the power of n. Okay, that's what we were seeing here. So we multiplied by 4. Our y values got multiplied by 4 squared because our equation had a square in it. Okay. Let's take a look at what happens with inverse variation. Okay, and then we'll kind of compare and contrast the two. So I'm going to work with the equation y equals 12x, or 12 over x, I'm sorry, because that's inverse variation. So I'm going to pick x equals 3. Well, if I plug in 3, 12 divided by 3 is 4, so I would get a y value of 4. Now let's say I'm going to double my x value. So I'm going to multiply by 2 here. So I'm going to put in a 6. Remember, the big question we're asking is, what does that mean happens over here? What happens to your y values? Well, when I plug in a 6, 12 divided by 6 gives me 2. So notice at this time, when I multiplied by 2 with the x values, my y values actually got smaller, which should make sense because it's inverse variation, right? So this gets divided by 2. So with inverse variation, the opposite operation happens. When you multiply the x's, the y's actually get smaller. They get divided by a number. Let's say I work with y equals 12 over x squared. And I plug in x equals 3. Well, that would give me 12 over 9, which I think comes out to be 4 over 3. All right. Let's take this x value and double it. So I'm going to plug in a 6. Well, that would be 12 over 36, which is 1/3. And I know these are fractions, and I know they're a little bit scarier, but the relationship between 4/3 and 1/3 is the 4/3 got divided by 4 here. Okay, so when we multiplied by 2, over here we got divided by 4. Divided by 4 is really the same thing as 2 squared. So we still have that squaring thing going on because our equation has a square in it. Okay, but the big thing to notice with inverse variation is that when you multiply on one side, you end up dividing on the other. Okay, now I'm not talking about solving the equation for k. I'm not talking about like when we multiply here to like cancel things out. I'm talking about the relationship between the x's and the y's. So when I do something to the x's, what happens to the y values? So to fill this part of the theorem in, when we're talking about inverse variation, if we come along and multiply x by a constant, so in this case that constant would be 2, when you multiply with inverse variation, then your y value gets divided by that c to the nth power. Okay, let's maybe work through a couple of examples, and hopefully that'll clear things up if you're feeling a little lost by all of that. So looking at example 1, the height of a float varies directly with the square of the length of the vehicle that supports the float. So that first sentence, that's that variation sentence that we always look for in one of these problems. So I'm going to start with a general equation here. So the height varies directly, so k times the square of the length of the vehicle. Okay. Now you'll notice, unlike the last set of problems we did, where the next step was always to plug numbers in, we're not given any actual numbers here. What it says is, suddenly this year's vehicles are 3 times as long as they used to be. And the 10 doesn't really matter, but I've suddenly taken the length of the vehicle and multiplied by 3. Okay, so I've taken that length and multiplied by 3. And my question is, what's going to happen to the h values as a result of that. Okay, how are my h values going to change? Well, because this is direct variation, whatever's happening over here is going to match what's happening over on the right. So if I'm multiplying over here, I'm multiplying the h value as well. But it's not just going to be 3 times as large, it's going to be squared, so it's going to be 9 times as large. So notice I didn't need to find the k value. The k value didn't do me any good here. All I was doing is saying, okay, if I tripled this number, what would be the effect on the h value? And you could play, I mean, you could plug numbers in if you really wanted to, but I don't want you to have to do that. I want you to be able to say, okay, if this number gets multiplied by 3, how is that going to affect the outcome? Okay, let's look at example 2. This question always throws me. The weight of a land animal varies directly with the cube of its femur diameter. So I'm going to stop right there, write my equation. So the weight varies directly, so k times the cube of the diameter of the femur. Okay, so W equals k times d cubed. Phoberomus, an extinct rodent, is an ancestor of the modern guinea pig. Its femur diameter is 18 times as large as that of a guinea pig. Okay, so this is 18 times larger than a guinea pig. What I want to know is what effect will that have on the weight? How will the weight compare to a guinea pig? If it's 18 times larger here, how is my weight being affected? Okay, well, it's direct variation, so I know multiplied is going to go with multiplied, right? Multiplication and multiplication going to go together. So I'm going to say it's times 18, but that 18 is going to be raised to the power of 3. So we know if we were to take the weight of a modern guinea pig and multiply it by 18 cubed, that would give us the weight of this beast. Well, we're in luck because this problem tells us what the weight of a modern guinea pig is. So that's exactly what I'm going to do. I'm going to say, I'm going to take that weight of 2 pounds and multiply it by the 18 to the power of 3. And we're going to find out that Phoberomus, this is a rodent, let's keep in mind this is a rodent, weighed approximately 11,664 pounds. A rodent that weighs 11,000 pounds. That's frightening. Google that. There's pictures of what it may have looked like. I mean, it's extinct, but it's a scary looking thing. So that's the idea. That's the idea with the fundamental theorem of variation, is we're asking ourselves, if we change one of the variables, how will that affect the other variable without actually using regular numbers in there? This one we did kind of use some regular numbers, but okay, let's try some inverse variation ones. So this one starts us with our what was I going to say? Our general variation equation. So we've got I equals k over d squared. And this is talking about the intensity of light as compared to the distance away from that object that you're sitting, okay? So you're working on your homework, sitting on your desk, and then you move to your bed. Your bed is 3 times as far away from your floor lamp as the desk. So my distance is increasing by a factor of 3. Again, this is not me trying to solve the equation. This is just me reflecting the relationship. This is what's happening to my distance. What I want to know is how will that affect the intensity of the light if I move 3 times as far away? Well, if I'm farther away, the intensity is going to go down, right? This is inverse variation. So I know that when I multiply on this side, I'm really going to end up dividing on this side, because that's how inverse variation works. They're opposites of each other. And it's not just going to be divided by 3, it's going to be divided by 3 squared. So there's a few ways you could write this. This is a little bit tricky to like say the sentence, but you could say it's like 9 times less intense. Or the other way to think about that, 9 times less would be like cutting it down by 9. So you could say 1/9 the intensity But either way, it's shrinking by a factor of 9. Whoops, sorry, I was talking and not spelling correctly. Intensity. Okay? So, fundamental theorem of variation is what's going on right there. Okay, so law of the lever, we're starting with that again. D equals K over W. Suppose you sit on one side and you're trying to balance with a child who weighs half as much as you do. Okay, so this is the important part here, half as much. So the weight is being cut down by 1/2. So we could think of that as being divided by 2. So if I take my weight and cut it in half, what is that going to do to the distance? Well, it's inverse variation. So when I divide on one side, that's going to lead to multiplication on the other side. And because there's no exponent here, it's just going to be multiplied by 2. So how far away should the child sit? They should sit twice as far as you are. They should take your distance, whatever it happens to be, and double it. So not a whole lot of math here. Really, a lot of the questions have to do with the relationships between variables. That's what I really want you to focus on here today. Okay, hopefully that's enough to get you through this lesson. You are working on section 2-3 today, and we will go over it as soon as I see you in class again.